Good morning and good afternoon. Thank you for attending the CXL Consortium, an overview of the Compute Express Link CXL 2.0's ECN webinar. Today's webinar will be led by CXL Consortium Technical Task Force Co-Chair Ishwar Agarwal and Software and Systems Workgroup Co-Chair Mahesh Naltu. Now I will hand it off to Ishwar to begin the webinar.
Good morning, good afternoon. Hi, my name is Ishwar Agarwal. I'm the CXL Technical Task Force Co-Chair. My co-presenter today is going to be Mahesh Natu, the CXL Systems and Software Workgroup Co-Chair. So this particular webinar is about the CXL Consortium's 2.0 specification ECNs. As you guys probably may be aware, CXL Consortium released the 2.0 specification, which introduced support for switching, memory pooling, and persistent memory, all while preserving industry investments in supporting full backward compatibility back in November 2020. And since then, based on member feedback, the consortium has made a number of significant improvements to the specifications in the areas of device management, RAS, security, memory interleaving, and others. And this particular webinar is going to review the key CXL 2.0 specification ECNs and the new usages that they enable. Okay, so with that little introduction, I'll go ahead and get started. So a brief introduction to where we are as an industry, right? So the way we think about it is that there was this era of cloud computing proliferation, and that is what I think about as generation one. And we are very much past that. It was very much accelerated with the pandemic, and we are very much in Gen 2, which is the growth of AI and analytics. And we are very shortly coming upon Gen 3, which is the ultimate cloudification of the network and edge. And with this kind of a trajectory that our industry is on, we have a number of new challenges as well as a number of new opportunities to scale to the next frontier of technology evolution. And that's really where CXL positions itself to be. So what is CXL? CXL is a consortium which is defining an open standard for high-speed communication. It's an open standard with 170 plus member companies today. It has most of the technology leaders that we know and recognize, some of whom are mentioned on this particular slide, but a whole lot of others as well. And it's a very vibrant ecosystem with very active participation in a number of technical work groups in the CXL consortium for introducing new features, new usages that are enabled by this new open standard for high-speed communication. So, quick introduction to what CXL really is. CXL addresses a number of challenges that our industry today faces, and that is the challenge for driving demand for faster data processing, especially in the context of next generation data center performance. It addresses the challenges associated with heterogeneous computing and server disaggregation. Another very, very key and very fundamental usage of CXL is in the arena of memory, specifically memory bandwidth and memory capacity. And all of these translate into this need for a next generation interconnect that stitches together all of these different usages, these different challenges into one coherent standard that can actually help scale all of these different opportunities. So CXL defines an open standard cache coherent interconnect that can connect CPUs, memory expanders, and accelerators. It leverages PCIe as the base and introduces 3 mix and match protocols that provide low latency access to cache and memory, as well as removes some of the complexity associated with traditional coherency and memory management. So when we think about a CXL device, we really think about a CXL device in the context of these 3 separate usages. These are essentially at a high level a way of binning these devices into the 3 nomenclatures that we use within the CXL consortium. These nomenclatures refer to devices as type 1 devices, type 2 devices, or type 3 devices. The type 1 device is a device which is an accelerator with coherent caches. And this is a type of accelerator where key usages are things such as partition global address space NICs, or devices that need to do remote atomics to host attached memory. In this context, the device uses CXL.io protocol and CXL.cache protocol. The second type of device is the type 2 device, which is a device which has coherent memory on the device itself. And typical usages for such types of devices are GPGPUs, FPGA, any type of accelerator that wants to do dense computation, right? And the protocols that this type of device uses, are CXL.io, CXL.cache, and CXL.mem. And the third type of device, which is last but certainly not the least, is type 3 device, which are really memory buffers. Now, memory buffers are really a way of extending system memory for either extending system memory bandwidth, or system memory capacity, or system memory capability, for example, adding new types of media, or media with different characteristics such as persistence. And this particular type of device is CXL.io, uses CXL.io, and uses CXL.mem. Okay, so when we talked about CXL and CXL 2.0, it enabled a number of these very advanced, very cool new usages with CXL, including pooling, switching, etc. But as we talked through the work groups, the member companies brought forth a number of different usages, a number of different features that they would like to enable with CXL 2.0. And to address that, CXL actually has a very robust ECN process. ECN in this particular context stands for Engineering Change Notification. And what this is a process to make changes to a release specification through a review and approval process, where these changes then get directly integrated into the baseline specification. And this flowchart briefly outlines that process. The key takeaway from this whole flowchart is that the ECN is something which is a change proposal that can be brought forth by any member company or one of the board of director companies. It goes through a number of review steps, including through the technical work groups. It has an overall review process through an overarching body called the Technical Task Force. Once it goes through all of the review through the technical work groups and technical task force, it's sent to the board of directors for approval. And once the board of directors has approved it, there is a review period for IP rights review as well as member review. And only after all of these thorough due diligence is done is an ECN then ratified and made part of the CXL specification. This robust process ensures that through all the steps of the ECN process, there is oversight as well as review, and we are able to take into account member feedback. Okay, so with that process having been said, now what we will go through next are a number of different key ECNs that were brought forth with CXL 2.0 to enable different types of usages. So the first ECN that we're going to talk about is called CXL error isolation. Now, error isolation is a particularly interesting and important topic for CXL. And the context over here is, how do we make this standard a more robust standard, especially in the event of unforeseen failures? As we in the technology industry recognize, failures are inevitable, and especially on the data center scale, this is something that we have to live with, but there needs to be a way to be able to contain failures to as small a granularity as possible in order to impact the least number of tenants that co-reside on a machine. And this particular ECN addresses exactly that problem statement. So the error isolation ECN describes and defines a way for graceful handling of uncorrectable errors at or below a CXL root port. The context here is the CXL specification 1.0 and 2.0 had two mechanisms already defined for error containment, and they were data poisoning and viral indications. However, through the review and feedback process, we found that the poisoning and viral indications did not cover all the usages that we would like to guard against in terms of error containment. Specifically, it did not cover error types which pertain to events such as surprise link down. Surprise link down could be for any reason. For example, let's say you have a memory buffer connected in a data center through a cable, and accidentally somebody kicks the cable out. Or if the device encounters a device-specific fatal error, what happens? Or if the device has, let's say there's a pooling device which has a security violation detected at a CXL memory controller, what happens? In the baseline specification, unfortunately, such errors may have propagated up all the way up to the CXL host bridge, and that would have led to a full system crash. The reason for a full system crash is because CXL is a coherent interconnect, and it's very hard to deal with errors that happen in a coherent system because the containment is very hard to guarantee. However, CXL error isolation allows for such errors to happen on CXL.cache protocol and CXL.mem protocol, and actually defines a way where such errors can be contained at the CXL root port and not allow the errors to propagate throughout the system. It also defines a mechanism for software to opportunistically recover from such an error without a full system reset. So the solution that the consortium came up with was a mechanism where error isolation would get triggered at a CXL root port in the event that there a request for timeout or if the link goes down, right? So a CXL.mem transaction is going to be tracked at the CXL root port if the root port implements CXL error isolation. And let's say a CXL memory request or request for data times out, the root port would trigger CXL error isolation, as an example. And once the error isolation is triggered, what the CXL root port then does is that it synthesizes responses for all new as well as pending requests on CXL.mem. And CXL.mem is just an example. The same thing happens on CXL.cache. And when we talked about CXL.mem transactions being handled gracefully by the root port, what that really means is that all the reads that were pending as well as new reads get synchronous error responses returned, and the writes get dropped and completed. That's very important because what that does is that it allows the rest of the system upstream from the CXL root port to essentially continue functioning, even though the root port and all the hierarchy below that root port has died. It also allows other CXL root ports that are co-resident on the same physical machine to also be functioning and not be impacted by an error that has occurred on a device below a different root port. So once we have handled the error at the root port, we also have mechanisms defined for software to investigate and log we have a mechanism for logging the error so that software can come and investigate what exactly happened. We also have mechanisms defined for software to then trigger a link reset bus and a bus reinitialization so that it can try to recover from such an error. The other nice thing about the way this particular ECN was defined is that this ECN only impacts the host. That means all of these mechanisms can be implemented inside the CPU, and it does not need any change in the CXL switch or in the CXL device. Okay. At this point, I'm going to ask Mahesh to take over and walk us through some of the other ECNs. Mahesh, do you want to take over from here?
Okay, thanks, Ishwar, and thanks for painting the big picture of what CXL is in the ECN process, right? That definitely helps with the technical details that I'm going to go into, right? Starting in the next slide. So actually, before we get into my material, there was one question on the chat that I wonder if you want to address. I think the feedback is the flow chart is not readable, and I believe they're referring to the ECN flow chart.
Okay. Yeah. Thank you for that particular question. We can try and make that flowchart available in a more readable format after the webinar.
Okay, so there's no other questions right now for your material, so I'll jump into memory interleaving and some other topics, right? Uh, so as you can see from the right-hand picture, a system can have a number of CXL devices, and as part of the CXL 2.0 spec work, we defined the ability to interleave memory devices. It's a pretty common capability that's available with, let's say, native DDI attached memory, where uh, the different DDI DIMMs are interleaved together to improve performance. So as part of the 2.0 spec, we defined methods to uh, implement 2, 4, and 8-way interleaving options. We didn't really want to go overboard and define too many options to begin with, and we thought we'll add new options as needed. Um, as Ishwar mentioned, there's just a lot of interest in the Type 3 and memory expansion usage model that we witnessed, right? Just phenomenal interest. So we realized after releasing the 2.0 specification that this particular area needs to be beefed up a little bit, and that's why this ECN came about. Right? So this ECN adds the options to uh, allow 3, 6, 12, and 16-way interleave capabilities, which means you can take up to 12 or 16, right, CXL devices and make them part of a single interleave stack. Again, the key reasons were these options are today available with native DDI. And so when CXL is used to expand the DDI capability or the native memory like bandwidth or capacity, it makes sense for CXL to have similar capabilities. And a lot of times also we notice that like system designers want to match the memory capacity with compute capabilities, uh, such as number of cores or maybe other aspects, the I/O channels. And going from 4 to 8 was quite a big jump for many of them, given the cost of the memory devices as well as the number of I/O lanes that they consume. So the 6-way, right, was considered a sweet spot between 4 and 8 that folks were interested in. The way this was defined was in a way so there's no impact to switches uh, and only impacts the devices and the host. Again, easier for the ecosystem to swallow this change as an ECN. Unfortunately, the 3, 6, and 12-way interleaving math requires doing a 3-way math, right? Which means that the hosts have to implement mod 3 like function to select 1 out of 3 or 6 or 12 targets. Right? Previously, with the 2, 4, and 8-way, life was simple. Host could just look at 1, 2, or 3 address bits and select the target. With the 3, 6, and 12, you have the added complexity of doing a mod 3, which is uh, extra work and not super trivial. The device also needs to do the matching, right? Computation, which is like a divide by 3 operation, which divide by 3, 6, or 12 uh, on the HPA to compute the local address. So again, affects both hosts and devices. And in order to limit the complexity, scope, and some other uh, uh, aliasing possibilities, right? When you're mixing a 2-way and 3-way math together, we also limited some combination that are supported. For example, this ECN describes what interleave options are available at different levels and how they can be combined to get either 3, 6, 12, or 16-way interleave at the device option. The base requirement that we had previously in that spec namely, uh, you must use contiguous address bits to select interleave. That remains in place. So, I mean, this is probably best illustrated with the example, right? So on the right-hand side, I saw an example where the host has 6 root ports. Each root port is attached to a CXL Type 3 device, and all these 6 devices are now interleaved together as a single interleave set. Again, I'm not showing 6 devices, but you get the idea at the bottom. The way this is done is that the host specific logic all the way at the top uh, implements a 3-way interleave, let's say at a 1 kilobyte granularity. This is affecting the address range 16 to 22 terabytes, right? So remember there's 66 terabytes of address range now, 16 to 22. Each device is 1 terabyte in size. And so 6 devices total, right, will give you 6 times 1, 6 terabytes of address space. So the host specific logic is going to pick 1 out of 3 host pages at 1K granularity using the MOR3 math I talked about. When it comes to a CXL host page, each of them has 2 root ports. So it's going to use the standard 2-way math to calculate which of the 2 root ports the transaction should go to. So it's going to either out to the left one or the right one in each case. So that gives you 3 times 2, 6-way, right, interleaving. And when the device gets the address, right, it'll see effectively a 6-way interleave at a 512 byte granularity, which means every 512 byte address, right, chunk is going to go to a different device, right? 0 to 512 will go to the first device, the next 512 bytes go to the second device, and so on and so forth. And after the 6 devices are completed, it'll go back to the device, first device. Standard interleaving scheme. Then I will show a little bit more complicated picture. This is an example of 12-way interleave and involves multiple levels. So again, at the host logic, we're doing a 3-way interleave at 1K, just like we did previously. Same address range, 16 to 22 terabytes. In this case, each device is half a terabyte in capacity. So half a terabyte times 12 gives you a total of 6 terabytes, right, for the address range. Again, at the CXL host page, the host page will select 1 out of 2 root ports, same logic as before. The additional step is that each root port sees a switch below it. So there's a total of 6 switches that are not shown in the picture, but you can imagine. And each switch now gets the same address range, 16 to 22 terabytes, and it's going to do a 2-way selection, meaning select one of the 2 downstream switch ports based on one of the address bits, which happens to be 250 bytes. So that will be address bit 8, and select the device below. So again, 3 times 2 times 2, and you end up with a 12-way interleave. And the device again sees a 12-way interleave at 256 bytes granularity, and it's going to divide by 12 math effectively to figure out the local address, because it's getting 1, right, out of every 12th 250 byte chunk, right, its way. Okay, so I think hopefully these pictures clarify how this works better than the language. The other interesting one, again, a good example of how we were able to get member feedback almost real time and react to it, right? So just a background, if you look at the CXL 2.0 spec, it states that a 2.0 a device is required to interrupt with the CXL 1.1 host. And the addressing scheme for the device changed when we went from a 1.1 spec to 2.0 spec for scalability and addition of switches. So in the 2.0 connection scenario, uh, the picture on the left, right, shows how the switch register layout looks like. Again, it's showing a simple device with a single PCI function for simplicity. And thanks for the feedback. And so the registers look pretty much like a standard PCI registers, right? So you have the config space here, has bar that points to the cache memory registers, and cache memory registers have things like RAS, link, and HDM, right? Standard stuff, right? Defined as 6 like 2 spec. The 2.0 spec, right, required that when the same device is connected to a 1.1 host, the register layout look quite a bit different, right? Uh, if you remember, 1.1 devices have the notion of this memory mapped RCRB space in the downstream port, and uh, that essentially points to the cache memory registers, and that points to all these other AS, link, and HTML registers together. And the config space only has bar and some DB6 registers, right? So if you look at the left versus right, some registers that appear in the config space here, now they need to be sent up into the memory space, and that morphing, right, the feedback from the uh, members that are implementing this, right, the IP vendors or the device vendors, was that this was particularly tricky. This was possible, but was particularly tricky and error prone. So what we did with that is we simplified the uh, the morphing to be very, very simple, right? So this ECN called 1.1 mode operation without RCRB essentially eliminated the requirement that the 2.0 device implement RCRB in order to interoperate with the 1.1 host. So if you look at what this ECN does, it allows the device to maintain the same address map that it had here on the 2.0 mode and take it, right, and map it the same way here. What we added was the device needs to be able to uh, return all ones when software attempts to read the RCRB space. That is how software determines that this device is a 1.1 device but is implementing the ECN. And it knows to look for all these other registers in the config space, right? Like a 2.0, right, device. Again, this was a simplification for the device designers, required a change to the software, but we were to intercept this in a timely manner before a lot of software was written. So this was made possible. If you had waited a couple of years or year for this, right, uh, there would have been a lot of legacy software around that assumed, right, the 2.0 spec behavior, and this would not have been possible. So it's really important for us to be able to react to member feedback, right, in real time and provide a solution as soon as possible. The other ECN.
Mahesh, there were some questions on the bridge. Do you want to take them now or at the end?
Sure. So let me take. So I can read them out. I can see them. So does
Yeah.
okay. One of the question was, does no RCIP requirement also mean no RCEC requirement? The answer for that is no. That's not what it means. So RCEC is required if the device is exposed as an RCIP, a root complex integrated endpoint, and in this picture, that aspect hasn't changed. So this device on the right-hand side needs to expose itself as an RCIP. So this link is still not visible to the legacy software because the downstream port above still has the same layout as 1.1. Therefore, you still need the host to implement an RCEC, and the errors from this device always go to the RCEC. There's no difference in behavior. Hope that answered the question. Yeah, if that didn't answer, then please post a follow-up question, and I'll try to answer that. I think the second one is on the previous slide. So the three-way interleave, yeah, I think the question is either three-way interleave only supported at the proprietary cross-host bridge level, or it's supported at each level, host bridge, USB, and device. So since we didn't want to affect switches and we didn't want switches to do the awkward three-way mod operation that does add latency and complexity, we limited the three-way math to only the host in a host proprietary logic and the device. So there is no support for three-way interleaving at the USP, for example, right? But obviously there's three-way interleaving support needed at the device in order for the device to translate the host physical address to device physical address. Okay, hopefully that answered the question. If not, please repost. So let me continue with the next ECN. Again, this is also a very interesting one. So as we saw, there was just a lot of interest in Type 3 devices, and as we saw a number of members looking into this option, few things became very clear. Right? That in order for ecosystem to use these devices effectively, they needed a standard-based and symmetric in-band and out-of-band configuration interface. Right? So in-band interface is important for OS to manage the device. Out-of-band interface is commonly used by the baseboard management controller to manage the device when OS is not running or in a manner that's OS independent. And both are sort of standard expectations in the data center these days. It was also important for these devices to be able to do time to market, which means they needed some uh, simpler design options. And there was also a lot of interest in the ecosystem to be able to take the current BMC firmware designs and being able to quickly spin those to take advantage of and manage the Type 3 devices. So when we looked at this feedback, we realized that we needed to implement a way by which these Type 3 devices could be managed out of band. So, I mean, again, if you're familiar with the 6L 2.0 spec work, we did define an interface for in-band management of the device. That is in chapter 8 of the 6L 2.0 spec, pretty extensive details as to how OS can manage the devices. It does things like media management for different medias, handles memory errors, right, update of the firmware, data at rest security, right, just to name a few things, right. So it's a pretty extensive set of capabilities that the OS can use to manage the device. So in order to meet these needs, what we did is we did something very simple, right? We decided to map the same messages or same command set that the OS had over to out-of-band interface, and the most uh, industry-wide used transport today is MCTP. So we essentially mapped the same messages over to MCTP, so allowing BMC to sort of issue the same commands uh, using MCTP transport without having to redefine the message type. So if you look at the picture on the right, what we had originally was things on the left. This is what the 2.0 spec had. We had the Type 3 device using CXL.io. We defined the mailbox interface that allowed the OS to send and receive messages to the device for things like managing the media, and the Type 3 OS driver, a generic driver, could do that, right, and use these messages and the mailboxes to manage these devices. What we added was for if the BMC or baseboard management controller, which is generally typically a microcontroller on the motherboard that is handling all of the outer band OS independent management, to be able to send the same messages over MCTP. And MCTP is a DMTF standard, and they are we collaborate very closely with DMTF on number of items, and this is one a good example of collaboration between these two standards bodies. So by wrapping these over to MCTP, MCTP messages can be sent over different interconnects, including PCI Express, SM bus. So we get all of those options pretty much for free, allowing the BMC to use existing methods to manage the Type 3 devices, right, in the system. So I think that was a pretty efficient way to address the problem, and the industry came together, the member companies came together to build a solution in a relatively quick time frame. So moving forward, so this was another interesting one, right? So we, in part of the 2.0 specification, right, we introduced the feature called IDE, and IDE stands for integrity and data encryption, and allows the CXL cache mem traffic that's flowing on the link to be encrypted and integrity protected, right? Which means that any modifications to that can be detected, and the data cannot be snooped, right, by, let's say, any interposers that are trying to observe the bus traffic and try to uh, potentially steal user data, right? So IDE will guard against that. What we could not do, again, just because of the time limit, is define how the software or the firmware will configure IDE. Right? As you can imagine, in order to encrypt and integrity protect, right? Both sides need a set of symmetric keys in order to process the data and encrypt it, right? So we didn't really have the flow defined as to how that is done. So this ECN sort of defines that by adding a set of messages. We call them CXL underscore ID underscore KM. And these messages are sent by the host software. It could be, or it could be BMC, for example, right, in some scenarios, to a device that supports IDE. And these requests are used to provision the keys, configure the keys, and then finally uh, ask the component to either start the IDE session or tear down an existing IDE session, right? So all of that management of the session is performed through these messages. Again, the requests and responses are protected. Again, it doesn't help you a lot if the keys are sent in plain text, right? Because, right, whoever can observe the keys can also observe the traffic that's going to be encrypted using those keys, right? So these messages are protected as well using, again, another DMTF standard called Expedia. So on the right-hand side shows a pretty impressive software stack, but again, it just shows that we are able to leverage most of the existing standards. So for example, if you look at all of the boxes that are colored white, those are DMTF standards. The sort of light blue are PCIe standards. So we're able to leverage all of that. The thing on the right, almost right hand, is the IDE protocol itself. These are changes to the protocol for encryption. They were part of the 2.0 spec. And the only piece we added was this new set of messages for configuring them. Everything else, we were able to leverage the existing industry ecosystem and right, just get things started. Again, it is really good to be able to leverage other standards because you can leverage the architecture, all the effort that has gone into making sure these specs and these interfaces are stable and maintained. And so I think a lot of right across industry collaboration across different standards bodies, including DMTF and PCIe, to make this possible. So going the other one, I think I think also probably familiar that compliance is a very essential part of any standard, right? The main purpose in life of a standard is to make sure components from different vendors can interoperate, uh, and they can only interoperate if they follow the spec as right intended, right? So compliance tests allow a component to be tested against the spec requirements and is essentially a key piece of allowing interoperability. So some of the things that were added in the compliance uh, to dedicated ECNs are include things like an option to inject memory errors, right? So CXL device defined a pretty robust RAS capabilities. I think if I went to poison and viral earlier, uh, but we didn't really have a way by which someone could compliance test those and make sure that device behaves the way spec intends. So by allowing the compliance test to inject errors, like things like errors in the data region, errors in the metadata areas, right, or being able to spoof health status changes, um, the, the device could be tested against those requirements. Similarly, there was new test being added, so device could be put into viral mode. Again, this was something that was already part of 2.0 spec, the viral mode, but there wasn't really a robust way to test that. And like some of these things we realize as we go on, as certain features in the CXL spec are pretty important, but at the same time, some it could be hard to get right. So that's where the compliance right work group focused on and identified these areas where they needed to sort of bolster the current compliance right, requirements uh, and cover this additional ground. There was also changes to how the compliance data object exchange is handled to provide more scalability. Previously, it was not possible to query some of the capabilities. This, the third ECN, the DO return value allows the compliance test to query what the device supports and then right can use those to further write other tests, right? There was also some simplifications to be made as we went to the current compliance test. We identified certain areas where we had defined some requirements for the device that were really hard to implement. So some of this was also allowing the devices to have an easier design option and get to the market quicker. CXL 2.0 also added a feature called QoS telemetry rather late in the cycle. So we didn't really have time to go develop the compliance requirements around that. So this was sort of a diving catch to add and capture that requirement in the compliance test cases. And one thing I want to make sure that the other ECNs that Vishu and I talked about, right, they all have relevant compliance, right, requirements added, right? So for example, when we introduced the interleaving or the MCTP ECN earlier, relevant sections to the compliance test were added to make sure these ECNs will be tested as we see devices implementing those ECNs.
Mahesh, there are a couple of questions on the chat window if you want to answer them now.
Sure. So I think one, I believe I already answered. The question was, what is BMC? So BMC stands for Baseboard Management Controller. That is often used to manage the system in an OS independent manner. It's generally a microcontroller with its own memory and its own firmware and its own subsystem, right? That's sort of isolated from the OS. And the second question is why are they indicated as SPDM messages in the IDE Establishment ECN? So they actually payload to the SPDM vendor-defined request and response messages. So yeah, this could be a matter of semantics. So SPDM vendor-defined request and response are defined by SPDM specification DSP0274 for vendor extension. So that's really what we mean there. If it's too confusing, again, please elaborate on what specific confusion it's causing, and we'd be happy to either provide a clarification either here or through the spec. Thank you. Okay, so I think we're coming to the end. So I want to just summarize a whole bunch of other ECNs. Again, not saying that these were not important, but we just have a large number of ECNs that it was not practical for us to go through all of them in the time allowed, right? So I have a summary of things that we didn't cover today, maybe at a future time. There's also, all of these are also posted on the CXL Consortium site. We'll be providing the link to it. And so I recommend folks who are interested to go visit the site, download the ECNs and look at the details and provide feedback if there's any. So the first one in the list is the what we call CEDT, lots of acronyms here, CEDT, CFMWS, and QTG_DSM. Right? So what this is in plain English is that these are the CFMWS is an extension to ACPI tables that allows the software to discover how the host address decoders are programmed. Right. So this allows software to figure out. So going back to this previous picture that we had. So CFMWS would allow software to, the firmware to notify the software that this particular address range, 16 to 22 terabytes, is configured in certain way in this decoder. So let's say at boot time, nothing is plugged in here, but all these show up later hot added. So the OS software can know this range is configured this way here, and now can assign addresses to these devices that show up later because it knows what addresses are going to be targeted to this range, right? So that's really what the CFMWS does. The other piece, the QTG, is just providing software primitives that allow the CXL2 QoS telemetry feature to be enabled, right? It allows the software to figure out which throttling group a particular device address range needs to be mapped to based on the platform policy. There were a couple things that we did to add design flexibility as, again, members started to design or think about how to implement the CXL devices or components. They were looking for areas where the spec was either too restrictive and causing complexity design that wasn't really needed, right? So the mailbox ready time allows devices to take longer than the fixed amount of time that specs say, right? I think specs say 2 seconds, right? Uh, they can take more than 2 seconds to get ready. Again, some devices made based on the inherent microarchitecture or the firmware design, right, may take longer. So this ECN allowed that option. The null capability ECN here also allows some flexibility to allow the component to jump over one of the header entry, right, if they need to, without really having to do complicated shuffling of pointers in the hardware. Right? So this was also a simplification of the option. The register located DVSec allows vendor extensions. There are certain areas where vendors wanted to innovate and add their own capabilities, but still leverage some of the base DVSec structure that CXL had defined. So that was the locator DVSec ECN. And I think this one I would have liked to cover in detail, but just don't have time for it. It's a very important one, be able to collect the component state. So this is extremely useful for RAS and debug. As you can imagine, the CXL components they're all new, right? A lot of new designs. Industry is learning, and in order to do debug any issues that may be discovered during the bring up or in the field, it is important to be able to observe the state of the component in the scenario of failure or a behavior that's unexpected, right? So this defines the standard commands by which a BMC or the host can request a component crash log, meaning if the component were to fail, uh, it would be able to sort of log some critical information about itself, so someone outside can figure out what may have happened, right? There's also a request for component to capture current state, current execution state. This is again useful for debug or right, bringing up a new system. So I think the last one is a pretty important step, and I think we found it's important to standardize this early on, so the devices that are designing, right, being designed today can intercept it and not have to invent vendor-specific mechanisms for these things. So allows for uniformity across the industry and debug practices. Okay. So just summarizing. So I think Ishwar did a pretty good job of going over what CXL Consortium is, and so again, want to highlight that the momentum is growing. As you can see, we have more and more members. I think the number of members, we're having a hard time keeping the count of the member count straight. If you can see, the number here is different than the one that Ishwar showed. Just have added new members over the last week or so, looks like. And we are being very responsive to industry needs. And that's really the reason why I think we are seeing the momentum, right? Is that, as you can saw from the ECN description, that we are able to quickly get to the problem that industry needs us to solve, right? Work through different work groups, build a proposal, and then come out with a solution, right, very, really quickly, and not have to wait for the next spin of the spec, right? It is we are finding that there's a lot of excitement in being able to use memory attachment or even persistent memory to the CXL devices. We have pretty robust driver software model. And so the call to action today really is, if you are not, please join the consortium. There's different levels at which you can join the consortium and contribute to this this movement, right? So again, if you have problems that need to be solved, or if you have solutions that you think you can offer to the consortium, yeah, this is the best way to do that, is by joining the consortium and contributing. Now I think we'll have time for Q&A.
Yes, so thank you, Mahesh. Thank you, Ishwar. So we will now begin the Q&A portion of the webinar. So please do share your questions in the question box.
There is one question there already that we can take.
Do you want to take that, Ishwar?
There is one question there already that we can take, which is how do we distinguish the original 2.0 spec versus 2.0 with ECN? Will the spec version be revised to be 2.1? Mahesh, do you want to take that?
I was hoping you would take that. But yeah, no, there is no plan to do a 2.1. I think we have the ECNs posted in the same spot as the 2.0 specification. And when we do the next spec revision, they will be rolled into the next spec revision. But there is no plan to do a 2.1.
Yeah. So yeah, in general, the process with ECN is that once the ECNs have been ratified, they are considered part of the baseline 2.0 specification or whichever the specification the ECN has been targeted at. So all of these ECNs that we're talking about today are ECNs to 2.0. So once the ECNs are ratified, they're posted separately, and whenever these the document containing the spec is revised, the ECNs are folded into it so that they're not in separate documents anymore. Other questions?
If you have any questions, please share them in the Q&A box. Well, seeing as though we have no additional questions, we can end the presentation here. So thank you, Ishwar and Mahesh, for sharing your expertise. The presentation recording will be available on the CXL Consortium's YouTube channel, and the slides will also be available on the CXL Consortium website. It is under the download the specification page, which will be hyperlinked in the YouTube recording. And we would like to encourage all our viewers interested to learn more about CXL to join the CXL Consortium, download the evaluation copy of the 2.0 specifications and all the ECNs, and engage with us on Twitter, LinkedIn, and YouTube. Oh, we do have a question here about, is there any support for OS X Linux for IDE?
So I would say a lot of the links work is happening in the open source community. I'm not aware of any code that's being upstream right now or patch that's been delivered that enables IDE, but I'm expecting that will happen pretty soon. As we start seeing designs that take advantage of IDE.
Just one additional question about where can we find the compliance tests?
The CXL spec has a chapter, chapter 14, that lists various compliance tests, and these ECN that we talked about sort of complement that, right? So I think the tests themselves, I like to find what the link is, but the content of what they plan to test, right, is in the CXL spec itself. Ishwar, do you know where the compliance tests themselves are posted?
I believe some of the content is under the compliance work group. They have some hyperlinks, but the content of the test is really spelled out in the chapters, as you correctly said.
And the latest version of the 2.0 with the ECNs are available on the CXL Consortium website. So it's computeexpresslink.org. When you go to download the specification page, you will be able to download all this 2.0 specification with all the ECNs as well. Okay, so once again, we would like to thank you for attending the CXL Consortium's an overview of the Compute Express Link 2.0 ECN webinar. Thank you. Good day.
Thank you.